Okay, sorry. Okay, so we continue with the.
Everybody's selfish. Screen.
So we continue the talks, and so now we have Julio Cesar Correa. He's going to talk about Sobolev type inequality in rectifiable varifolds. Sorry.
Thank you very much, Juliana. Thank you very much to the organization for this opportunity, and thank you all for being present today. I'm going to talk about Sobolev type inequalities in a geometric context. What I mean in a geometric context is what I'm going to consider its various underlying settings more than the usual ones. So before to continue and state my result, I'm going to give to you a walkthrough very Sobolev type and what I mean to change the underlying set. For example, the classic one, everybody knows, proved by Gallardo, Nienberg, and Sobolev, all works independently and beautiful works, says that if I give you an open set and a infinity function compactly supported in the open set, I know that for every p between 1 and n excluded, there exists a universal constant, which I will name k, depending only on n and p, such that satisfies this inequality, right? Okay, later in the 76, Oban proves the following. What happened if instead of an open set, I consider a complete Riemannian manifold? What happened is that to get this kind of inequality, I have to have some geometrical abstractions. What I mean by geometrical abstractions is that if I give you a complete Riemannian manifold with bound geometry, which is to say that the curvature is bounded by above and the injectivity radius always is positive, I can assure that given epsilon greater than 0, there exists some constant a depending on epsilon and q, such that for every function in W1Q holds the following inequality. This inequality has to be proven that the k is the same as in the Euclidean one and is the less constant satisfying this inequality. Furthermore, in the early 2000 was proven that this constant has to be sharp in some sense, but I'm not going to mention. And finally, what inspires our work is a work by Michael and Simons, independently by art. In fact, it was stated in a broader context of geometrical objects called Varifolds. I'm going to talk here about submanifolds, just to introduce you what they prove. But in general, it was proven in Varifolds, which is a broader class of geometric object that I will introduce later. They proved that if I give you a k-dimensional submanifold of the Euclidean space with mean curvature vector h assumed to be in LP, then for any C1 function, non-negative, I can prove, they prove the existence of a constant which is universal. I mean, it just depends on the dimension of my submanifold such that that inequality holds. That inequality is basically a Sobolev type inequality, as we know, for the P1 star, right? Where P star is the critical Sobolev exponent. But notice that when you look at here, it will appear some correction due to the mean curvature. And this agrees with the Alban results. In the case in the Q-dimension, it means when k is equal n, right? So what we prove is this result for a rectifiable manifolds in Riemannian manifolds. What it means? It means that I will consider some geometrical objects embedded in an arbitrary quoted in an arbitrary Riemannian manifold with certain conditions. Namely, I give you a Riemannian manifold with a metric C2 or more regular, this will be important, and satisfy some geometric condition. Again, I call it bounded geometry, which is that the sectional curvature is always bounded by above and positivity radius of injectivity. And if I give you a k-rectifiable variable, defining in this manifold M with generalized mean curvature again in LP and a density condition. I will explain this later. I know that for a given function, C1 function compactly support in my variable, whatever it means, I have this inequality. This inequality varies from the Michael-Simon-Molar one, because in the sense that we have a term, blue one, C star, which is a geometric constant. And it's rather natural, right? Because here we consider functions in which the correction term will be given by the curvature. Now what we get is correction terms given by some geometrical constants. But okay, I'm going to highlight some things here that we are working on the rectifiable variable setting and associate to them a generalized mean curvature. I will explain first to talk about the proof of this result, a little bit of what they are, these things. To define rectifiable variables, first I have to talk about rectifiable set. What's a rectifiable set? Rectifiable set can be viewed as a generalization of a C1 manifold, embedded manifold, right? How going to do this? This is basically, okay, you have the definition there, but you can view it as a Frankenstein monster made by Lipschitz patches, you know? One important thing that have these Lipschitz patches is that by Rademacher's theorem, every Lipschitz function is differentiable almost everywhere, then I can define a tangent plane to it, or an approximation tangent plane. How I will define? How I will use the derivative of the Lipschitz function, which exists almost everywhere, and I define this tangent as x, as shown there, which turns to be a subspace of the tangent space at the point y, right? To give you some examples, I make some draws here. I'm not very good drawer, but I expect everybody understand. My first example is two simplex in the R3 space. It's clearly that we can say that this is a rectifiable set because it's a patch made for image of planes, right? And if you notice, we are allowing certain kind of singularities for the set. Learn more intrinsic one is if I give you a sphere and I consider a piecewise C1 curve on it, it will be again a rectifiable set, but only my ambient is not more R3 or Rn or any Euclidean space, rather a manifold itself. And finally, I have an example that I like it because it shows the spirit of these sets. As I'm not very good drawer in R4, this is a sketch of the trajectory of body being sucked by a black hole. This also will be a rectifiable set, right? Okay, but I'm talking about rectifiable variables, not rectifiable sets. What is a rectifiable variable? Rectifiable variable is basically a rectifiable set which allows densities. What I mean by densities? Okay, the definition is there. It's basically equivalences class of pairs satisfying some measure theoretic conditions, right? But you can view it by the two examples here. You can think in two planes, parallel each other, connected by a catenoidal neck. So if you make the height dividing these planes going to zero, and the neck collapse itself, you will converge to a plane in some sense. But these planes, it not be a regular plane because you have mass from the upper plane and mass for the lower plane. Then you will converge to a plane counted 2 times, right? This is what I mean density that are allowed in our rectifiable sets. Another example is the one on the right. It's when you think on an open book, which is basically a plane being intersected along a line by several planes. Again, if I give you every plane some mass, some density on it, the intersection line will have a lot of mass more than every plane, right? Okay, but what is the important that we can allow these kind of densities is that associated to every variable, I can define a radon measure. A radon measure via this definition, which is simply integration. Sorry, an A is missing there. But if I want to measure some set A, I will integrate it against the Hausdorff-K dimensional measure of the function density, okay? But okay, I produce, in some sense, a weak formulation for C1 remaining submanifolds. So what? What it came to, what it's worth for it, right? It works because I can define what is the first variation of a variable, which is simply defined as to be as the formula. If I give you a vector, a C1 compactly supported vector field, I can define the first variation as integration over the set S of the tangential divergence of the vector field, where the tangential divergence is simply the trace operator of the nabla of the derivative of the vector field composed with the tangent at the point X of the set S, which I say exists almost everywhere, right? Then I have two questions to notice something for you. And notice that this, I can extend every vector field C1 compactly supported vector field by C0 vector field. So I can extend this first variation delta to be a well-defined function, right? Thus, if I consider the total variation of this functional, I know what the Riesz representation theorem and the Lebesgue differentiation theorem, the Radon-Nikodym theorem, basically every theorem concerning differentiation of measures in measure theory, I know that there exists a function that I will call hg to be a function from M to the tangent, locally integrable such that my function will have this phase. I can express it in the terms as the sum of these two measures, right? And this function is what I will call the generalized mean curvature of the varifolds. Sorry about it. Furthermore, notice that again by the Lebesgue differentiation theorem, if I assume to the function to be LP, this term in red will be vanished because you don't have singular part on them. So summarizing, in summary, I give you a complete remaining variable. I define what is a chi-rectifiable variable, which is a suitable generalization of C1 or C infinity manifolds embedded in our intrinsic manifold M, and I give them a notion of generalized mean curvature, such that this formula holds. Okay, so I have a few comments about it. First of all, notice that if you take S or rectifiable set to be a submanifold and theta of multiplicity function to be 1, I'm talking about the submanifold. So this formula gives me the first variation of the area in the classical Riemannian geometry. So I construct some geometrical objects which are well behaved under minimization problems of the function of the area, right? And this will be important per se, right? Another question that I have to you and to me in particular is, okay, how can I define a generalized mean curvature of a manifold of a variable, if I instead of thinking in a manifold per se, in an intrinsic manifold, I will embed it in some Euclidean space. And if I can do it, what can I say of its first variation? And this is why I highlight in red at the beginning of my result, the C2 metric, because this came to me when I was on the ICM, talking to the professor Camille Delelis, and he highlighted us how important to be the metric to be C2 rather than C3, because we are assuming C3 metrics for conveniences purposes, right? And this is why, if you consider a remaining manifold of metric of class C2 alpha for every alpha greater than 0 less than 1 or more regular, you know about the Nash-Inverting theorem that there exists an isometric immersion, and that isometric immersion has bounded second fundamental form. So you can apply the old theory to this, but okay, we can relax this C2 alpha metric. And this is important when you working on geometric analysis in problems with variable metrics, because you want the metric to be the less regular possible, right? Another problem, and I try to picture it, it's the following. If I give you submanifold rather than a variable, but it works basically equally. In the picture, I have my varifold in black, I have my submanifold sigma in purple, and I depict the tangent plane at the point C of my varifold M in red. So if I give you a vector field, C1 compactly supported, I know that I can break it in a tangential part. It means living in my tangent space in red, and some normal part, which will be expressed in terms of the normal to the manifold, which exists by the embedding that I'm considering. So if I calculate the divergence of it, I will have a tangential divergence and a subnormal part, depending on the second fundamental form of the varifold, of the manifold, right? And this second part will give me this curvature vector, this mean curvature vector, but the first part, I don't know how to deal with it. So if I expect to have a first variation of these embedded objects, I will expect to this divergence, this tangential divergence will to be 0. And this is not always be 0. If the vector field was always tangent, okay, it will be 0. But okay, we are allowing, besides to relax the metric, we are allowing another broader class of vector fields which analyze it. So let's talk a little bit of my result and how I prove it. My result, rather than a Sobolev direct to be a Sobolev inequality, and this is beautiful because what we actually prove with some monotonicity result of the density of the varifold itself. And this is a geometric result. And the implication in the analytic realm via the Sobolev inequality is something marvelous to me. I don't know how to say it anyway. But okay, my result concerning the monotonicity of the varifold was the following. If I give you a Riemannian manifold, again with bound geometry, meaning to this that I will assume the sectional curvature to be bounded by above and positive radial injectivity, and I give you as a k-dimensional varifold defined on my manifold M with generalized mean curvature, and I consider an special ansatz for a vector field. This is why I need to consider a broader class which allows C0 vector fields, because the vector field X that I will consider is a radial perturbation, where R is the distance function induced by the metric, and gamma epsilon is a sequence of functions, regular is needed, which converge to some characteristic function. If you look at this vector field X, you can see that this vector field is not differentiable at C or 0. So this is why I consider this weakened class of varifolds instead of submanifolds. Okay, so if I computing this, the first variation of the variable along this vector field, what I have is that there exists some geometric constant with this inequality holds. If I change the blue parts, if I erase the C star in blue and change the inequality for equality, I am in the case of submanifolds presented by Allard and Michael and Simon. This is where we actually use the geometry of the ambient manifold to produce this constant, and this is the result what we get basically, because the proofs of the Sobolev inequality came a little bit straightforward, if you want to say it. And look at this. If you set here epsilon to 0, set epsilon to 10 to 0, you know that we are in the case that you converge into some characteristic function in some distributional sense. So if after make epsilon to going to 0 and integrate over an appropriate interval, right, I have to be aware that never going outside this R0, which is my bound of my injectivity radius, because out of there I don't know what happens, right? Okay, when I do epsilon going to 0 and integrate, I get this inequality. Using some calculus trick, this is a proposition that I'm not going to tell you precisely here, but if you were curious, you can see it in the paper. You can prove this inequality in which we change the regime of the poles to be, instead of an arbitrary sigma, to be 5 times rho, and it will appear some 5 over there, which tells us that if we apply the Vitalis 5 covering lemma, we can take this inequality to the whole support of the function, okay, at least when it's greater than 1. And finally, by an appropriate rescaling, I can deduce my Sobolev inequality, in which the constant is that, and as you will see, it does not depend on k. And this is all that I have to say to you today. Thank you very much. I want to finish with this beautiful photo of the night sky here in the south.
Okay, thank you, Julio, very much for the very nice talk. So now, if anyone has any question, and please share with us in the chat, or you